Okay, think about this for a second. The dyes used for our clothes, they consume enough water every year to nearly fill the Mediterranean Sea. Twice.
Wow.
And the synthetic rubber in most car tires, that stuff sticks around for centuries.
Yeah, it's pretty sobering when you look at the sheer scale of it.
It really is. So let's unpack this because those numbers, they paint a really stark picture of why sustainable alternatives in textiles and rubber aren't just, a nice idea. They're becoming essential.
Absolutely. And what's fascinating, I think, is how deeply woven these industries are into our everyday lives. I mean, from the clothes we wear to how we get around, their impact is just enormous.
Right.
So when we talk about making them more sustainable, we're really talking about a fundamental shift.
Yeah.
It has really far-reaching consequences.
Exactly. And today we're aiming to go beyond just the usual eco-friendly fabrics you might hear about. We want to dive deep into this world of rubber-based sustainable textiles and their increasingly critical role in industrial applications. We're talking tires, conveyor belts, even materials used in defense and aircraft. Serious stuff.
And if you zoom out a bit, you can see that the progress here isn't just about, being environmentally friendly for its own sake.
Right.
It's also about using our resources much more intelligently, minimizing waste, and ultimately creating a more robust and, efficient industrial foundation.
Okay, so our mission for you today is pretty straightforward. We want to cut through the noise, get past the jargon, and really extract the most vital and hopefully some surprising insights into this field. It's evolving so quickly.
Yeah, it really is.
And we've got a fantastic resource to guide us through this. It's a brand new academic review called Rubber-Based Sustainable Textiles and Potential Industrial Applications, literally just published this May 2025.
And what makes this review so useful for our deep dive today is just how comprehensive it is. It really covers the whole spectrum. Everything from how you select environmentally sound fibers and sustainable rubber sources to developing eco-friendly additives, the actual manufacturing processes involved, a huge range of applications.
Tires, belts.
Exactly. And crucially, how we can get better at recycling and, maybe even more importantly, upcycling these really complex materials at the end of their life.
Okay, so think of this as our expert-curated shortcut for you to understand how these two massive industries, textiles and rubber, are increasingly trying to embed sustainability right at their core.
Right.
So let's jump right in. What's the real underlying driving force behind this big push towards sustainability in both these areas?
Well, I'd say there are two main drivers, really. First, there's just this significant surge in environmental awareness. And that's not just among us as consumers, but within the industries themselves, too.
Okay.
And secondly, there's the undeniable urgency to drastically cut our carbon footprints. Traditional textile production, for example, is incredibly resource-intensive, uses vast amounts of water, energy, chemicals, and similarly, many conventional rubbers come from petroleum, a non-renewable resource. Plus, their production often involves processes that aren't exactly, gentle on the environment.
It really hits home when you think about the entire life cycle, doesn't it? I mean, from getting the raw materials out of the ground to eventually throwing the product away. The conventional ways just carry this huge environmental burden.
Precisely. And that's exactly why we're seeing this growing emphasis on integrating sustainable textiles into rubber-based products.
Sure.
It's not just some niche trend anymore. It's becoming a really key factor in how we design and manufacture so many things we rely on daily. Think tires on our cars, conveyor belts in warehouses, even those specialized materials for defense applications.
Okay, now, when we talk about making these materials more sustainable, it seems like it all has to start with the basic building blocks, right? The fibers.
That's right.
But it's not just about finding something green, is it? Performance surely has to remain a top priority.
Oh, absolutely. You've hit the nail on the head there. Choosing eco-friendly fibers demands this really careful balancing act. You need to consider performance. Things like strength, durability, flexibility, alongside its sustainability profile. So, how easily does it biodegrade? Can it be recycled effectively?
Right.
You can't, for instance, make a heavy-duty conveyor belt out of something that just falls apart when it gets damp, no matter how eco-friendly it might seem on paper.
Makes perfect sense. So let's dig into some of these natural fibers. Some are making a comeback, others finding totally new industrial uses. Flax, for example. That's not just for linen shirts anymore.
Not at all. Flax fiber is increasingly popping up in automotive interiors. Think things like door panels, dashboards, even the backs of seats.
Really? Why?
Well, what makes it attractive there is its lightweight. It's a surprisingly good strength-to-weight ratio, and it actually helps dampen sound, too.
Interesting.
And if you compare it to traditional materials like, say, glass fiber, producing flax needs less energy, and it's much easier to recycle afterwards. Plus, because it's lighter, using it in cars can genuinely help improve fuel efficiency.
Ah, okay.
It's a fantastic example of where being sustainable also leads to better, or at least different, performance benefits.
That really illustrates that synergy well. Okay, what about jute? My mind immediately goes to those, rough burlap sacks.
Yeah, that's the common image, but jute has much wider potential. Its high tensile strength, combined with the fact that it's biodegradable, makes it a really excellent option for packaging. And we're talking beyond basic sacks here, more towards robust industrial packaging solutions. And it's also used quite a lot in geotextiles.
Geotextiles, what are those exactly?
Think of them as fabric-like materials used in construction and civil engineering. They help stabilize soil, prevent erosion, sometimes even suppress weeds.
Ah, okay.
And in those roles, jute offers a genuinely sustainable alternative to the plastic-based materials often used.
And hemp seems to be everywhere these days, doesn't it? From clothes to building materials. What role does it play in this industrial, textile, and rubber world?
Well, hemp brings a few things to the table. It has impressive strength, a natural resistance to mold and pests, and a relatively low environmental footprint during cultivation. It doesn't need loads of pesticides or water.
Right.
So in industrial uses, it's being explored quite actively for composites, various technical textiles, and even as reinforcement in eco-friendly construction stuff like insulation or concrete mixes.
And we probably shouldn't forget some of the others mentioned in the review, like Rami, Abaca, banana fibers.
Exactly. Rami, which is known for being exceptionally strong and durable, is finding its niche in industrial textiles where longevity is really key.
Yeah.
Think protective workwear, things like that.
Okay.
Abaca and banana fibers, maybe less common currently, but they show real promise as sustainable reinforcements in both automotive parts and rubber-based composites. And of course, cotton is still a major player in workwear, what the industry calls cloth tech, mainly because it's breathable and biodegradable. Even silk finds a place in high-end home furnishings or home tech, where it offers that blend of aesthetics and a long lifespan.
So nature definitely provides some great options, but what about synthetic fibers? I mean, they've been the backbone of so many industrial applications because of their performance characteristics. Can they become more sustainable too?
That's a really critical question. You're right. Synthetic fibers like polyester, polypropylene, nylon, they've dominated industrial uses because they're just so durable and perform so well in demanding conditions.
The downsides.
Exactly. Their reliance on petrochemicals, the fact they don't biodegrade, that poses significant environmental challenges. And that's before we even get to the whole microplastic pollution issue.
Yeah.
However, the industry isn't standing still. There's a lot of active innovation happening to try and make these fibers more sustainable.
Tell me more about that. I know there's been a lot of talk about recycled polyester, RPET.
Right. Recycled polyester, or RPET, which mostly comes from recycled plastic bottles, is a prime example, making it require significantly less energy and water compared to producing virgin polyester from scratch. And obviously, it helps divert a huge amount of plastic waste from landfills and potentially oceans. Now, there have been some concerns raised about things like BPA potentially leaching from recycled plastics.
I've heard about that.
Yeah, but certified recycling processes now include pretty strict measures and testing to minimize that risk.
Okay. And what about other key synthetics, like nylon and aramid fibers, the stuff in Kevlar vests and things?
Well, nylon, which is valued for its abrasion resistance and strength, is used all over the place. Industrial hoses, tire cords, conveyor belts, you name it. And initiatives like Econi, which actually recycles nylon waste like old fishing nets and carpets back into high-quality nylon yarn, are definitely gaining momentum.
That's good.
And aramid fibers, like Kevlar and Nomex, they offer just exceptional strength and flame resistance, indispensable for protective textiles. Now, while they're synthetic, their incredibly long service life and really demanding uses actually contributes to sustainability by reducing how often things need to be replaced.
So it sounds like the focus with synthetics is kind of twofold. Either find effective ways to recycle them or develop more sustainable ways to produce them in the first place.
Precisely. We're seeing some really exciting innovations like using bio-based monomers. Think of the fundamental building blocks of these plastics coming from renewable sources, like plants, instead of oil.
Like bio-peat.
Exactly. Using bio-derived terephthalic acid to make bio-peat is one example. Chemical recycling tech is also advancing. The goal there is to break down the synthetic polymers right back to their original chemical components, the monomers, so they can be reused again and again, creating a truly circular system.
That sounds ideal, but tricky.
It is tricky and not widespread yet, but it holds huge promise. And then you have these important green certifications, things like GRS, Global Recycled Standard, Okotex, Blue Sign. These provide assurance that specific environmental and human safety standards have been met throughout the production and sometimes recycling processes.
Right. Seals of approval, basically.
Kind of, yeah.
Yeah.
They help manufacturers and consumers identify more responsible options.
This is all really interesting, but the review also mentions something called advanced eco-friendly fibers. What makes these different from the sort of traditional natural and synthetic ones we've just discussed?
Yeah, these are often newer materials, maybe more cutting edge, that have been specifically engineered with sustainability as a core design principle right from the start. Tencel, which you might also know as lyocell, is a fantastic example.
Okay, Tencel. What's special about it?
It's made from sustainably harvested wood pulp, but the key is the production process. It uses what's called a closed-loop system, meaning that almost all, like 99.8% of the solvents and the water used in the process are recovered and reused over and over again. This massively minimizes waste and emissions, and it avoids using harsh, toxic chemicals you sometimes see in other fiber production.
Wow, okay. That sounds impressive.
It really is, and what's also remarkable is that Tencel doesn't compromise on performance. It has high strength, even when it's wet, excellent durability, and it absorbs moisture really well, all while needing significantly less water to produce than, say, conventional cotton.
And circularity.
Yes, they've even developed something called Refibra technology, which incorporates recycled cotton waste back into the production of new Tencel fibers. So it's actively building that circularity in. It's not just about being greener, it's fundamentally rethinking resource use, showing you can have high performance and near zero waste together.
That really does sound like a significant leap forward. And the review mentions industrial uses for lyocell too, not just clothes.
Absolutely. Its strength and durability make it really well suited for things like reinforcing rubber in tires, for use in anti-vibration components in machinery or vehicles, and even as high-performance linings in protective gear.
And bamboo. That's another one often touted as eco-friendly.
Yeah, bamboo fiber is definitely noteworthy.
Yeah.
Its main eco-credential is its rapid growth and ability to regenerate quickly after harvesting.
Right.
While we might know it more from clothing or homewares, bamboo fiber-reinforced polymer composites are being explored for industrial uses too. Things like wind turbine blades, construction elements, automotive parts, because they offer this interesting combination of strength, low density, and biodegradability.
Okay, so summing up on fibers then. When manufacturers are making these crucial choices about which eco-friendly fiber to go with, what are the absolute key factors they need to weigh up?
The review really boils it down to a few critical considerations. First, obviously the specific performance needed for the end product. You can't compromise there.
Number one.
Second, the cost of the fiber itself. Economics always play a role. Third, a really comprehensive look at its overall environmental impact across its whole life cycle, from raw material to disposal.
Okay.
Fourth, its potential for biodegradability and recyclability, what happens at the end of life. And finally, just how well it actually fits the intended use case.
Can you give an example?
Sure. Like we discussed, Kevlar's incredible tensile strength makes it the go-to for bulletproof vests. Nylon's specific properties, particularly nylon 6 sticks, known for its balance of strength, heat resistance, fatigue resistance, and good adhesion to rubber, make it a strong choice for tires. And cotton's comfort and breathability make it logical for workwear. It's about matching the fiber to the job.
Right. Matching the fiber to the specific demands of the application. Makes sense. Okay, so fibers are one huge piece of the sustainability puzzle. But the review title specifically mentions rubber-based sustainable textiles. Let's shift focus now to the rubber itself. Where are the sustainable options coming from in that sphere?
Yeah, the push to move away from petroleum-based synthetic rubbers is just as significant as it is for textiles, really, driven by very similar environmental concerns.
Right.
And fortunately, there's quite a bit of research and development happening, looking at both alternative natural rubber sources and ways to make synthetic rubber more sustainable.
Okay, natural rubber. I assume the main source is still the classic rubber tree, Hevea brasiliensis.
Exactly. Hevea brasiliensis, the source of what we just call natural rubber or NR, still dominates the market. It accounts for, what, something like 46% of global rubber production? And for good reason, it has fantastic mechanical properties.
Like what?
High tensile strength, excellent resistance to fatigue, really strong resistance to tearing. It's great stuff.
But
The heavy reliance on plantations in very specific geographical areas, Southeast Asia mainly,
right.
makes the supply chain vulnerable. And there's the ongoing threat of diseases like leaf blight affecting these trees. These are major drivers in the search for alternative natural sources.
And the review mentions a couple of interesting alternatives, guayule and Russian dandelion.
Yes, guayule is a woody shrub that actually thrives in arid and semi-arid regions like the U.S. Southwest or Mexico. Extracting rubber from it is a bit more complex than tapping a tree, and the rubber itself has slightly different properties, usually lower molecular weight, less gel content.
Which affects performance.
It can affect things like elasticity, yeah. But it's proving to be a viable and sustainable alternative, especially for non-dynamic applications. Think medical gloves, linings, insulation materials. It's a good option for those regions.
And the dandelion, that sounds quite unusual.
The Russian dandelion, Taraxacum coxsacus, is another intriguing possibility. Its roots contain a surprisingly high amount of rubber, and the mechanical properties can be quite comparable to Hevea rubber.
What are the advantages?
Well, it has a relatively short cultivation cycle, just a few months, compared to years for rubber trees. And it can grow in temperate climates, which could potentially lead to more localized, decentralized rubber production, reducing transportation impacts.
But there must be challenges.
Oh yeah, absolutely. Current challenges include achieving consistently high yields per hectare and developing really efficient harvesting and extraction techniques. It's promising, but still needs work to scale up.
It's really fascinating to think of these different plants becoming sources for something as ubiquitous as rubber.
Okay, what about sustainable synthetic rubbers? Is that even a possibility given they usually come from oil?
It's definitely a realistic prospect and a major focus of research. You're right, traditional synthetic rubbers have given us incredible versatility and performance tailored for specific needs, but their environmental baggage is significant.
So what's the alternative?
The focus now is on developing alternatives that reduce that reliance on fossil fuels and have a lighter environmental touch. One promising area is terpenes.
Terpenes, like in pine trees.
Exactly. Terpenes are naturally occurring compounds found in lots of plants. Pines, citrus peels, eucalyptus, even lemongrass. Their chemical structure actually bears some similarity to the building blocks of petrochemical-based elastomers, like isoprene.
For example, a terpene called bermyrcene, which you can get from conifers, can be polymerized to create polymyrcene elastomers. And these show properties quite similar to conventional synthetic rubbers like SBR, styrene butadiene rubber, which is used heavily in tires. So potential there for greener tire components.
That sounds very innovative. What about actually using biomass like agricultural waste or sugars to create the components of rubber?
That's another really exciting, rapidly developing area. Researchers are working hard on producing rubber-like materials from monomers derived directly from biomass. Key building blocks like isoprene and butadiene.
Wow.
Using biotechnology. Things like fermentation of sugars or chemical transformations of agricultural waste products to create these fundamental rubber components. The big picture goal here is to establish a much more circular economy for elastomers, slashing the carbon footprint in the process.
Again, challenges.
Yeah, same story, really. Improving production yields, bringing down the cost to be competitive with petrochemical routes, and ensuring scalability are the main hurdles right now. But the long-term potential is definitely substantial.
Okay, so we're seeing sustainable alternatives emerging for both the textile fibers and the rubber itself. That's great. But what about all the other ingredients? The stuff they mix in to make the final material work properly, like fillers for strength, plasticizers for flexibility, antioxidants to stop it degrading. Can those be sustainable too?
Yes, absolutely. The push for sustainability definitely extends to these crucial additives. Traditional options often come from petrochemicals or sometimes raise concerns about health or environmental impacts. So the focus is squarely on finding and developing greener alternatives that can, ideally, maintain or even enhance the performance of the final rubber composite.
Okay, let's take fillers. I know carbon black has been the standard in the rubber industry for, well, forever. What are the sustainable alternatives being looked at?
Silica is probably the most significant sustainable alternative filler, especially in tires. Using silica instead of, or along with, carbon black helps reduce the rolling resistance of the tire.
Which
directly translates into better fuel efficiency for the vehicle and therefore lower emissions. Interestingly, it also tends to improve a tire's grip on wet roads.
Okay. But is producing silica itself sustainable?
That's a fair question. While silica production does have an energy footprint, using sustainable sources like ash from burnt rice husks can significantly lower the greenhouse gas emissions compared to making traditional carbon black. You might have heard of Michelin's green tires. They heavily feature silica and have demonstrated real-world fuel savings.
Right.
We're also seeing more research into nanofillers, like nanosilica or nanoclays. The idea is that because they're so small, you need less material to get a significant performance boost.
And natural clays.
Yes, certain types of natural and modified nanoclays, like smectite or montmorillonite, are showing real promise as sustainable fillers. Studies using them in SBR, that's styrene butadiene rubber, have shown significant improvements in mechanical properties like strength and durability.
Why do they work so well?
It's down to their structure. These clays often have a layered structure that can interact really effectively with the rubber polymer chains at a nanoscale, creating a stronger overall matrix. There's also research into combining different fillers like natural rubber mixed with sepiolite, another type of clay, and carbon black showing even better properties. It's about finding the right synergistic mix.
Okay, plasticizers, they make the rubber more flexible, right? What are the sustainable options there?
Exactly. Traditional plasticizers like phthalates have come under scrutiny due to health and environmental concerns. So bio-based oils derived from vegetable sources are being actively explored. Things like soybean oil, castor oil.
Do they work as well?
They can offer comparable performance while reducing that reliance on fossil fuels. Epoxidized vegetable oils, particularly from soybeans, have shown real promise. They seem to provide good mechanical properties in the final rubber product and have a lower environmental impact profile compared to many traditional plasticizers.
And protecting the rubber from breaking down over time. Antioxidants.
Correct. Traditional antioxidants are often amine-based, and again, there can be potential environmental or health issues associated with some of them. So researchers are looking at bio-based antioxidants.
For plants.
Yes, derived from plant polyphenols. You find these in things like green tea extract, grape seeds, olive leaves. These natural compounds can be effective at preventing the oxidative degradation of rubber, potentially with safer byproducts. But the main limitations right now are often cost and establishing reliable, large-scale supply chains for these plant extracts.
Okay, even the vulcanization process itself, the thing that gives rubber its bounce and toughness, is getting a sustainability makeover.
It is. Zinc oxide, or ZNO, is a very common activator used in vulcanization. But there are environmental concerns about zinc leaching into soil and water.
So what's the alternative?
One approach is using nano-ZNO. Because nanoparticles have such a huge surface area relative to their volume, you need much less nano-ZNO to achieve the same activation effect as conventional ZNO. That directly reduces the amount of zinc used and potentially leaching out later.
Are there other options besides nanozinc?
Yes, alternatives like zinc chelates, which bind the zinc more effectively, and even accelerators derived from biological sources are under active investigation as well.
Wow, this is a really comprehensive shift towards sustainability across the board. So, okay, we're developing sustainable textiles, sustainable rubber components, and even sustainable additives. How do these all come together to create the actual industrial materials we've been discussing?
Right, that brings us neatly to the world of textile rubber composite materials themselves. These materials play this really crucial, though often hidden role in so many industries, transportation, material handling, you name it.
And what makes them so useful?
Well, they often provide a really cost-effective alternative to using purely fiber-reinforced polymers, especially when you need high flexibility and good resistance to impacts. The rubber matrix is key here. It helps enhance the material's fatigue life when it's subjected to repeated stress or loading, which is obviously critical in things like tires. And, as we've discussed, by incorporating sustainable textiles like jute or hemp into these composites, you can lower the overall environmental impact and sometimes even the cost of the final product.
So it's a real synergy happening between the properties of the textile reinforcement and the rubber matrix. But the review did mention they might not always match the performance of more advanced composites in some areas.
That's a fair point, yeah. Textile rubber composites might not be the best choice for applications needing the absolute highest levels of stiffness or resistance to extreme temperatures. In those cases, things like carbon fiber reinforced epoxies might still be necessary.
So it's about choosing the right tool for the job.
Exactly. The material selection always comes down to the specific performance requirements of the application. It's a balancing act between performance, cost-effectiveness, and increasingly sustainability.
Okay, and how are these composites actually made? What are the typical manufacturing steps?
Generally, the manufacturing process involves about 4 key stages. First up is rubber preparation, often called compounding.
Mixing everything together.
Pretty much. This is where the raw rubber is thoroughly mixed with all those additives we talked about, the fillers, plasticizers, antioxidants, vulcanizing agents, accelerators, everything needed to achieve the target properties for the final rubber compound. Each additive has a specific job.
Okay, step 1, compounding. What's next?
Step 2 is composite assembly. This is where you integrate the compounded rubber with the textile reinforcement. Common techniques include calendaring, like rolling or pressing the rubber compound into the fabric, ensuring good penetration. Or extrusion, where rubber is forced through a shaped die onto the fabric. Or lamination, which involves bonding layers of rubber and fabric together, maybe with heat and pressure. The method used can definitely influence the final composite properties.
Got it. Assembly. Step 3.
Consolidation and curing. Here, you apply heat and pressure to the assembled layers. This promotes strong bonding between the rubber and the textile, and it initiates the vulcanization process in the rubber, giving it its final elastic properties. Precise control over temperature and pressure during this curing stage is absolutely critical.
Okay. And finally?
Finally, there's post-processing. This can involve trimming off any excess material, maybe applying surface treatments to enhance wear resistance or reduce friction, cutting the composite into specific shapes or sizes, sealing edges to prevent fraying, or even adding textures for a better grip or aesthetics. Things like coatings or using lasers for precise cutting fall into this stage.
Okay, that gives a good picture of the manufacturing process. Now, with these sustainable textile rubber composites becoming more available, where are we actually seeing them being used out there in the industrial world?
Oh, the range of applications is remarkably broad. Tires, as we've mentioned several times, are a huge one. That synergy between the rubber matrix and the textile reinforcement is just essential for tires.
What exactly?
It provides the needed strength to contain the air pressure, the flexibility for a comfortable ride, the durability to last thousands of miles. It influences fuel efficiency through rolling resistance, helps dissipate heat buildup, and contributes massively to overall handling and safety.
And specific textiles are used for specific parts of the tire.
Yes, absolutely. Different textile materials are used in different tire components depending on the job they need to do. You'll find nylon 66, polyester, viscose, lyocell, aramid fibers, even carbon fibers in some high-performance tires. Each brings unique properties: strength, fatigue resistance, heat resistance, adhesion to rubber that enhance the tire's overall performance. There was even a study mentioned comparing the fatigue resistance of polyester versus nylons in tire cords, showing how material choice impacts longevity under stress. And interestingly, those more sustainable options like viscose and lyocell are being actively looked at as alternatives for certain components.
Right.
You also find textile rubber composites in things like chafer strips, which protect the part of the tire near the wheel rim, and in bead wraps that anchor the tire to the wheel. And alongside these textiles, you have that carefully formulated mix of rubbers, natural rubber, SBR, polybutadiene, isoprene, plus reinforcing fillers like silica and carbon black. Rubber resilience, its ability to bounce back, is particularly key for ride comfort and durability.
Okay, tires are a massive application. Conveyor belts seem like another big one that relies heavily on these materials.
Absolutely. Conveyor belts are really the unsung heroes of moving materials around in countless industries: mining, agriculture, logistics centers, manufacturing plants, you name it.
And why are textile rubber composites so good for this?
They offer that crucial combination of high load-bearing capacity, resistance to impacts and tearing, which is vital in rough environments like mining, the flexibility needed to run continuously over rollers, and they can even help reduce noise and vibration compared to, say, metal chain conveyors.
Does the material choice depend on the type of conveyor?
Yes, often it does. For instance, the distance the belt needs to cover plays a role. Lighter materials might be fine for shorter runs, while longer, more demanding applications will need textiles with higher strength. Historically, the materials have evolved too, from cotton in the early days to rayon, and now mostly synthetics like polyester, polyamide, nylon, and sometimes aramid for really heavy-duty belts, each offering better strength and resistance to moisture and degradation.
And the construction.
Typically, they involve multiple layers or plies of fabric, often with specific weave patterns for strength and flexibility, all embedded within a matrix of various synthetic and natural rubbers, chosen for properties like abrasion resistance or maybe oil resistance, depending on what's being conveyed.
Now, I was a little surprised to see defense products listed as a key application area. How are these composites used in the military or defense sector?
Yeah, it might seem less obvious, but textile rubber composites play a critical role in quite a variety of defense applications. Think protective gear, inflatable structures like boats or shelters, and other specialized equipment.
Like bulletproof vests.
Exactly. In body armor, layers of rubber-coated textiles can be used to help absorb and dissipate the energy from a bullet impact, working alongside the main ballistic fibers. There's even research mentioned using rubberized quarried coconut fiber as a potentially cost-effective component for protection against lower-caliber threats. Combining high-strength fabrics like Kevlar with rubber matrices has definitely been shown to improve overall ballistic performance.
And beyond vests.
Well, think about inflatable boats and rafts used for military operations. They need to be incredibly tough. Often they use nylon textiles reinforced with natural rubber to get high puncture resistance and durability. They also need to perform reliably in extreme temperatures and resist damage from UV light, salt water, and general abrasion. Rubber composites are ideal for that.
Okay.
And another key area is chemical and biological protective suits. Here, the rubber matrix acts as the primary barrier against hazardous substances, while the textile reinforcement provides the necessary strength and tear resistance for the suit itself. High-performance fabrics like Kevlar might be incorporated for enhanced protection levels in really demanding scenarios.
And even aircraft structures. That sounds like an incredibly demanding environment. Performance must be absolutely critical there.
It is, absolutely. Fabric rubber composites play a crucial, though maybe small, role in specific aircraft parts, like door seals. These seals have to maintain integrity and function perfectly under extreme pressure differentials and temperature changes, and endure countless opening and closing cycles. Wear resistance is paramount.
So how are they designed for that?
These composites often use specific types of textiles, maybe denser fabrics on the surface for wear resistance, and more open, reticulated fabrics internally for reinforcement. This combination creates what's called an anisotropic composite, meaning its properties are different depending on the direction you measure them.
But rubber itself can be tricky to work with in engineering terms.
Extremely. The review mentions the challenges posed by the hyperviscoelasticity of rubber. That's a fancy term, but it basically means rubber exhibits large deformations under load. Its behavior isn't linear. Double the force doesn't necessarily mean double the stretch. It's very sensitive to temperature, and it shows effects like stress softening known as the Mullins effect, where its stiffness changes after the first time it's stretched.
So how do engineers account for all that?
They use pretty sophisticated modeling and analysis techniques. Things like micromechanical modeling to understand behavior at the fiber-rubber interface, developing complex, nonlinear constitutive models to predict how the composite will behave under real-world loads, and using things like Arrhenius equations to factor in the effects of temperature on materials' properties over time. It's complex stuff.
It certainly sounds like it. So just to recap the benefits we've touched on, these textile rubber composites offer incredible versatility, right? You can tailor properties for specific needs. You mentioned soft robotics using silicone rubber composites as an example.
Exactly.
They offer durability, leading to longer service life, like those mining conveyor belts. There was even a study comparing their impact resistance favorably to steel cord belts.
Right. Durability is key.
They allow for weight reduction, which means energy savings in things like lightweight vehicle parts or even high-performance bicycle tires.
Yep. Lighter weight is often a big plus.
They have excellent corrosion resistance, making them suitable for harsh environments, marine applications, chemical plants.
Very true.
They provide effective vibration damping, which helps reduce noise in things like vehicle structures.
Good point. Noise reduction is important.
You can customize them by choosing specific fibers and rubbers, like that Kevlar silicone example in aircraft.
High degree of customization.
And crucially, linking back to our main theme, they offer increasing potential for sustainability through the use of recycled or bio-based materials. We saw examples like flooring made from old conveyor belts or sustainable materials in footwear.
Exactly. And that point about incorporating recycled materials is becoming more and more central, especially with the growing focus on building a circular economy.
Which leads us perfectly into the final, really critical aspect.
Yeah.
What happens to all these materials when they reach the end of their useful life? Recycling and upcycling seem absolutely essential if we want to create a truly sustainable system here.
They are absolutely vital. The pressure is mounting across both the textile and rubber industries for much greater sustainability, and robust recycling and upcycling initiatives are key to that.
Why so critical?
Well, they're essential for reducing the sheer volume of waste going to landfills, for conserving valuable natural resources, and for significantly lowering the carbon dioxide emissions that come from producing virgin materials from scratch.
Okay, let's break it down. Starting with textiles. What are the main ways textiles are being recycled or developed for recycling currently?
Broadly, the approaches fall into a few main categories. There's mechanical recycling, chemical recycling, thermochemical methods, and biorecycling.
Mechanical is just shredding it up.
Pretty much, yeah.
Yeah.
Physically breaking down the textiles. The downside is it often results in shorter, weaker fibers, so the quality isn't as high, and it's less effective for blends of different fibers, or particularly for textile rubber composites, because of contamination from the rubber, and the fact that thermoset rubber can't just be melted down and reformed easily.
Okay, chemical recycling.
Chemical recycling aims to break down the textile polymers right back to their basic molecular building blocks using chemical processes. This potentially yields higher quality recycled fibers and shows more promise for separating mixtures, like cotton and polyester blends, maybe using enzymes to selectively break one down.
But it's not widespread yet.
Not widely available commercially, no. Still requires development and scale up. Then you have thermochemical methods, like gasification. This can convert pretty much any fiber type into syngas, which is a useful fuel or chemical intermediate, but it's not a closed-loop process back to making new textile fiber.
Right, and biorecycling.
This uses things like enzymes, biological catalysts, to decompose the fibers. It's seen as promising, especially for natural fibers or blends like cotton polyester, but its application specifically to rubber-containing composites is still largely unexplored territory.
The review did mention some interesting real-world examples of textile recycling and upcycling efforts.
Yes, it did. Companies like SuperCircle are working to create actual textile-to-textile recycling loops, connecting brands with waste streams and the recycling infrastructure needed. They even help design clothes for recyclability and set up take-back programs.
That sounds proactive.
It is. There's also the PESCO UP project mentioned, focusing on using digital tech for better sorting and separation of textile waste, which is a huge bottleneck currently. And upcycling initiatives are important too, transforming waste into higher value products. Textile Recyclers Australia, TRA, was mentioned for upcycling worn garments into new textiles.
And big brands.
Yeah, big retailers like Fast Retailing, who own Uniqlo, are doing things like recycling down and feathers, offering in-store repair and remake services, and finding uses for non-recyclable textiles, like turning them into insulation or soundproofing materials.
So it sounds like there's definitely progress on textile recycling, but still some major hurdles.
Oh, absolutely. The sheer complexity of modern textiles, blends, coatings, trims, non-textile bits like zips and buttons makes separation and processing really difficult. We also lack sufficient recycling infrastructure in many places. Plus, the cost and the environmental footprint of the recycling processes themselves need careful consideration. And finally, getting consumers aware and participating actively in collection schemes is crucial for success.
Okay, now let's switch to the rubber side. Recycling used tires, for example, just seems like a massive challenge. Where are we with that?
It is a huge undertaking, yeah. And it's a really critical area for sustainable waste management globally. The main goal of rubber recycling is obviously to divert end-of-life rubber products, especially tires, from landfills, and to conserve the resources embedded in them.
What are the key technologies used?
Several approaches exist. Devulcanization is a major focus. That aims to break the sulfur crosslinks that were formed during vulcanization, the ones that give rubber its elasticity. If you can break those links, you can potentially reprocess the rubber.
How do they do that?
Various methods, using heat, thermal, mechanical force, chemicals, even specialized microbes. One example mentioned used supercritical CO2 with a chemical called diphenyl disulfide. There are also thermomechanical processes, often using equipment like co-rotating twin extruders that use both shear forces and heat to break down the rubber network and create materials called thermoplastic vulcanizates, or TPVs.
Any other methods?
Microwave and ultrasonic energy are being explored too. They offer the potential to selectively target and break the crosslinks without degrading the main rubber polymer chains as much. Chemical methods can aim to break the rubber down further, maybe back to monomers or other useful chemicals. And pyrolysis is another route, heating the rubber without oxygen to produce oil, gas, and a solid residue called char, all of which can have value.
And just getting the rubber ready for recycling from old tires.
Right. There are standard methods to get crumb rubber from end-of-life tires, or ELTs, things like grinding them up at ambient temperatures, or freezing them with liquid nitrogen first, and then grinding, cryogenic grinding, wet grinding processes, sometimes using ozone to help break down the surface. It all aims to produce rubber particles of various sizes.
Okay, but what about the quality of this recycled rubber? Can it really replace virgin rubber in demanding uses?
That's the million-dollar question, really. The review points out that the mechanical properties of recycled rubber are often inferior to virgin rubber. Part of the reason is chemical changes that happen during processing or aging, like the formation of conjugated double bonds during reversion, which can negatively affect performance.
So sintered rubber, for example.
Yeah, rubber made by just pressing and heating recycled rubber granules, sintering, often shows lower strength compared to composites made with virgin rubber. The final properties depend heavily on things like the processing temperature used, how long it was sintered for, the exact composition of the recycled granules, RG, and the particle size.
Does adding more recycled rubber always make it worse?
Generally, yes. Increasing the amount of recycled rubber tends to decrease most mechanical properties, although sometimes elongation at break can actually improve. Interestingly, though, one study found that adding certain low molecular weight organic acids could actually enhance the properties of sintered natural rubber granules. So there are ways to potentially improve it.
But overall, it's mostly used in less demanding things.
Currently, yes. Recycled rubber is finding growing use in applications like flooring, mats, seals, some automotive accessories, footwear soles, roofing materials, insulation, maybe playground surfaces, and solid tires for things like forklifts. But its use in high-performance products like new passenger car tires is still pretty limited due to these quality constraints. Getting recycled rubber to perform at the same demanding level as virgin compounds remains a major engineering challenge. That's really the holy grail.
But there are efforts to improve the quality and find higher value uses. Upcycling.
Oh, absolutely. Companies like Ecotech Recycling were mentioned for having patented devulcanization technologies, aiming specifically at producing higher quality reclaimed rubber. And there's significant research into upcycling waste rubber, transforming it into much more valuable materials like carbon nanotubes, or using the pyrolysis products as value-added fuels or chemical feedstocks.
So the perception is changing.
It is evolving, yes. Recycled rubber is moving away from just being seen as a cheap, low-grade filler towards being recognized as a potentially valuable component in sustainable manufacturing. While its use in brand new tires might still be limited, recycled rubber granules, RGs, are definitely being used more widely in other molded and extruded products and in things like landscaping mulch or additives for asphalt.
But just like with textiles, rubber recycling faces its own significant challenges too.
It does. The complexity of rubber products themselves, all the different additives, fillers, sometimes embedded metal wires or textile cords, makes processing difficult and variable. Devulcanization itself is inherently hard because those sulfur crosslinks are very stable. The methods often require a lot of energy and can risk degrading the rubber polymers anyway.
And quality control.
Quality and consistency of the reclaimed rubber can be variable, often containing impurities or defects, making it less reliable than virgin material. And finally, the economic viability of some recycling processes, coupled with regulatory hurdles or lack of strong market demand for recycled content in some sectors, also need to be overcome for wider adoption.
Well, this has been an incredibly insightful deep dive into this whole world of rubber-based sustainable textiles. We've covered a lot of ground.
We certainly have.
From the key drivers pushing the shift to the really fascinating array of innovative materials and technologies being developed both for the textiles and the rubber and the additives too.
Right, the whole system.
We've looked at the diverse and pretty critical industrial applications where these composite materials are used, and finally tackled that absolutely essential piece, recycling and upcycling, trying to close the loop.
And what's really remarkable, I think, is seeing how these two fields, textiles and rubber, which might seem quite distinct, are increasingly converging with this shared goal of sustainability. It's driving some significant innovation in both material science and manufacturing processes.
It really is. So a final thought perhaps for you listening. As you look at the products around you, your clothes, your car tires, maybe even the floor mats, take a moment to consider the journey of the materials they're made from. Think about the potential for a more circular economy. And maybe ask yourself, What specific innovations do you think hold the most promise for making these essential materials truly sustainable in the years ahead? Or, thinking about that convergence we just mentioned, what other unexpected collaborations between different industries might hold the key to future breakthroughs in sustainability? Definitely something to ponder.
Yeah, and perhaps it also raises the question for all of us as consumers, as engineers, as industry players. How can we actively support these ongoing developments and really help pave the way for a more sustainable future for these vital materials?